Databases serve as the backbone of modern information systems, providing a structured and efficient way to store, manage, and retrieve data. Understanding the fundamentals of databases is essential for anyone involved in back-end development, as it forms the basis for building scalable and reliable applications. This section will delve deeper into the fundamentals of databases, covering key concepts such as data modeling, schema design, indexing, and normalization. Data modeling. Data modeling is the process of defining the structure of a database and the relationships between different types of data. It involves identifying the entities, such as customers, products, or orders, and the attributes associated with each entity. For example, in a customer database, the entity might be customer, and the attributes might include name, address, and email. Data modeling also includes defining the relationships between entities, such as one-to-one, one-to-many, or many-to-many relationships. Schema design. Schema design involves creating a blueprint for the database, including the tables, columns, and constraints that define the data model. The schema defines the structure of the database and the rules that govern the relationships between different types of data. A well-designed schema is essential for ensuring data integrity, performance, and scalability. Schema design also involves choosing appropriate data types for each column, setting constraints to enforce data integrity, and optimizing the database for performance. Indexing. Indexing is a technique used to improve the performance of database queries by creating efficient data structures that allow for fast retrieval of records. Indexes are created on one or more columns of a table and are used to quickly locate records that match a specific query condition. By creating indexes on commonly queried columns, developers can reduce the time it takes to execute queries and improve overall database performance. However, indexing also comes with overhead, as indexes need to be updated whenever the underlying data changes. Normalization. Normalization is the process of organizing data to minimize redundancy and improve data integrity. It involves breaking down large tables into smaller, more manageable tables and defining relationships between them. Normalization helps reduce data duplication and ensures that each piece of information is stored in only one place, thereby reducing the risk of inconsistencies and anomalies. There are several normal forms, each with its own set of rules for eliminating redundancy and ensuring data integrity. Data migration and transformation. Data migration involves transferring data from one database to another, often during the process of upgrading or replacing an existing system. Data transformation involves converting data from one format to another, such as converting data from a legacy system into a new format that is compatible with a modern database. Data migration and transformation are complex processes that require careful planning and execution to ensure that data is transferred accurately and without loss. Concurrency control. Concurrency control is the process of managing simultaneous access to shared resources in a database, such as tables or rows. It ensures that multiple users can access and modify data concurrently without interfering with each other's transactions. Concurrency control techniques include locking, multi-version concurrency control, MVCC, and optimistic concurrency control. These techniques help prevent data corruption and ensure the consistency and integrity of the database. Data security. Data security is a critical aspect of database management, as databases often contain sensitive information that needs to be protected from unauthorized access, modification, or disclosure. Database security measures include authentication, authorization, encryption, and auditing. These measures help ensure that only authorized users have access to the database and that data is protected both at rest and in transit. Relational databases have long been the dominant choice for storing and managing structured data in software applications. However, the rise of new data types, increased scalability requirements, and the need for flexible data models have led to the emergence of non-relational databases as viable alternatives. In this section, we will explore the differences between relational and non-relational databases, their respective strengths and weaknesses, and scenarios where each type of database is most suitable. Relational databases are based on the relational model proposed by Edgar F. Codd in the 1970s. They organize data into tables, with each table consisting of rows and columns. The relationships between tables are established through primary and foreign keys, which enforce referential integrity and ensure data consistency. Relational databases use structured query language, SQL, as the standard language for querying and manipulating data. Strengths of relational databases. 1. Data integrity. Relational databases enforce strong data integrity constraints, such as unique keys, foreign keys, and check constraints, which help maintain data accuracy and consistency. 2. ACID properties. Relational databases adhere to the principles of atomicity, consistency, isolation, and durability, which ensure that transactions are executed reliably and that the database remains in a consistent state even in the event of system failures. 3. Mature ecosystem. Relational databases have a mature ecosystem with robust tooling, extensive documentation, and widespread support from developers and vendors. 4. Complex queries. Relational databases excel at handling complex queries involving multiple tables and complex join operations. SQL provides a powerful and expressive syntax for querying and manipulating relational data. 2. ACID properties. Relational databases adhere to the principles of atomicity, consistency, isolation, and durability, ACID, which ensure that transactions are executed reliably and that the database remains in a consistent state even in the event of system failures. 3. Mature ecosystem. Relational databases have a mature ecosystem with robust tooling, extensive documentation, and widespread support from developers and vendors. 4. Complex queries. Relational databases excel at handling complex queries involving multiple tables and complex join operations. SQL provides a powerful and expressive syntax for querying and manipulating relational data. Weaknesses of relational databases. 1. Scalability. Traditional relational databases face challenges in scaling out horizontally to handle large volumes of data and high request rates. Scaling relational databases often requires expensive hardware upgrades and complex sharding or replication strategies. 2. Schema rigidity. Relational databases have a rigid schema that requires predefined table structures and fixed data types. Modifying the schema can be cumbersome and may require downtime for maintenance. Non-relational databases, also known as NoSQL databases, provide a flexible and scalable alternative to relational databases for storing and managing unstructured or semi-structured data. Unlike relational databases, which adhere to a rigid schema, non-relational databases allow for schemaless or schema-flexible data models. Strengths of non-relational databases. 1. Scalability. Non-relational databases are designed to scale out horizontally to handle large volumes of data and high request rates. They employ distributed architectures that can seamlessly add new nodes to accommodate increased load. 2. Flexible data models. Non-relational databases support flexible data models, including key-value pairs, document stores, column family stores, and graph databases. This flexibility allows developers to adapt the data model to the specific needs of their application without being constrained by a fixed schema. Weaknesses of non-relational databases. 1. Lack of ACID compliance. Many non-relational databases sacrifice some of the ACID properties in favor of scalability and performance. This can lead to eventual consistency and the possibility of data inconsistencies in distributed systems. 2. Limited query capabilities. Non-relational databases may lack the expressive querying capabilities of SQL-based relational databases, especially when dealing with complex join operations and ad hoc queries. 3. Learning curve. Non-relational databases often require developers to learn new data modeling techniques and query languages, which can result in a steep learning curve for teams accustomed to working with relational databases. 4. Tooling and ecosystem. While the non-relational database ecosystem has grown rapidly in recent years, it may still lack the maturity and breadth of tooling available for relational databases. Developers may encounter limitations in terms of monitoring, debugging, and administration tools.
In the realm of modern software applications, database management systems, or DBMS, serve as the backbone for storing, managing, and retrieving data efficiently. Let's delve into the world of popular DBMS like MySQL, PostgreSQL, and MongoDB to uncover their unique characteristics, strengths, weaknesses, and common use cases. Starting with MySQL, an open-source relational DBMS developed by Oracle Corporation, known for its user-friendly interface, scalability, and robust client-server architecture. MySQL supports multiple storage engines like InnoDB, MyAm, and Memory, making it a versatile choice for developers and organizations. Moving on to PostgreSQL, a powerful open-source relational DBMS renowned for its advanced features, compliance with SQL standards, and robust support for ACID transactions. PostgreSQL's extensibility, data integrity, and community support make it a preferred choice for diverse applications. Lastly, MongoDB, a popular NoSQL DBMS offering flexibility, scalability, and ease of use through its document-oriented data model. MongoDB's strengths lie in its high performance, developer productivity, and support for dynamic schemas, making it ideal for applications with evolving data needs. Query languages are essential tools for interacting with databases effectively. SQL, the standard language for relational databases, provides a structured syntax for querying and manipulating data across various DBMS like MySQL, PostgreSQL, and Oracle. Let's explore the key components of SQL queries and data manipulation operations. SQL queries consist of components like select, from, where, group by, having, and order by, enabling users to retrieve, filter, group, and sort data efficiently. In addition to querying data, SQL supports essential data manipulation operations like insert, update, delete, and merge for maintaining data integrity and consistency. NoSQL databases like MongoDB, Cassandra, Redis, and Elasticsearch employ specialized query languages tailored to their data models and storage mechanisms. For instance, MongoDB uses MQL, Cassandra uses CQL, Redis operates with key-value access patterns, and Elasticsearch utilizes Query DSL for complex data retrieval and aggregation.